Are you studying GCSE Physics? Here at Physics Online, I've made hundreds of videos for every aspect of every course, all organised by exam board and then by topic. For a small one-off payment, you get access for 3 years, and at $9.99 it's far cheaper than you might expect. That's the same price as 3 pod coffees or 3 Big Macs. Gain access to all videos to learn the physics that you require for your exams. Put simply, for less than a tenner, you get on-demand access to all the videos that you'll need in GCSE Physics. Hello everybody, welcome to the 12th of May for this GCSE live stream. So today what we're going to be doing is we're going to be looking at acceleration. So this is very much how much an object's velocity will change, that might speed up or it might slow down or even change direction. So hopefully everybody out there is doing well. It's great to see so many people on the chat already and so many people liking the video. So hello to everybody who's put comments in so far. If you haven't already done so, you can find the worksheet over at GCSE Physics Online, so you can find hundreds and hundreds more videos there and past papers and everything else to help you with your GCSE Physics. If you go to the COVID-19 or the homeschool page, you'll find the lesson for today. You can download the worksheet if you haven't already done so, or you can just kind of play along at home and answer questions as the live stream is continuing. So yeah, actually, somebody said today was supposed to be the GCSE biology paper. So we are now in exam season, and I suppose although it is bad at the moment in terms of being at home, there's maybe a bit of lack of motivation. It's probably better than having to sit in a real exam, isn't it? But, you know, here we are. This is where we are. So let's do some questions about acceleration. So the first bit is naming the units for... Name the units that each of the variables in the equation are measured in. So acceleration given in meters per second squared. Change in velocity is meters per second, and time is in seconds. Okay, write down the equation using symbols rather than words. So there's a couple of ways of doing this. We can say the acceleration is equal to the change in velocity divided by time, or we can say it's equal to v minus u divided by t. Okay, so both of these are appropriate. And the key thing here is that v is going to be equal to the final velocity and u is the initial or starting velocity. Okay, so it's often, if you're using v minus u, just make sure it's very clear that it's a u and not a small v, or you can use delta v to be that change in velocity. So let's use this equation here to calculate the acceleration of an object going from rest to 14 meters per second in 10 seconds. So a lot of the time you'll have questions where something is maybe starting static, or it maybe ends at rest, and therefore we often have 0 meters per second, even though it's not given to you as a number in the question. So rest just means 0 meters per second. So the acceleration is going to be the change in velocity divided by the time. So the final velocity was 14, the initial velocity was 0, and that took 10 seconds. So that's just 14 divided by 10, which equals 1.4 meters per second squared. Okay, and this one here is something which is really important. Don't forget to have your squared term for the acceleration. Somebody just asked about which one is in the AQA formula book. I can't remember, to be honest. I think they might use this one here. Okay, I think probably this one here is a better equation to use than this one here. Sometimes you might see it as delta v over delta t, but basically this is what I'm going to use, a equals v minus u over t. Okay, next we're going to have an object decelerating from 100 to 5 in 38 seconds. So here, a is equal to v minus u divided by t. Now the final value of velocity is 5.0 and the initial value was 100. So we're looking at 5 take away 100 divided by 38. Okay, so 5 take away 100 is going to be minus 95, and that's divided by 38, giving an answer equal to minus 2.5 meters per second squared. And here, the fact that we have a negative symbol, that just means we have a deceleration. Okay, Cool, hopefully that's good. Hello, Mr. Seaton. It's great to see some teachers on here as well. If anybody has any questions that they want to put into the live stream, just ask away. I know that other students can answer them. I can answer some of them as I see them. And yeah, basically, I think that that's something. Hold on, let me just get rid of that. Yeah, if you're a teacher on here, that's brilliant. And if you've got any advice for any students, please just put some stuff down there. So we've got a negative value here because acceleration can have a positive or a negative value because it is a vector quantity. And that means it doesn't just have size, but it has direction as well. So here we've got something decelerating, so it's a negative acceleration. Right, the next one, we've got an object accelerating from rest to 120 meters per second in 1.5 minutes. So again, a equals v minus u over t. The final value for velocity is 120. The initial value was 0. And the time, if it's 1.5 minutes, we have to convert that to seconds. So 60 seconds in a minute. So in 1.5 minutes, there are 90 seconds. And then this is going to be 120 over 90, which is 12 over 9, which is 1.3. So although we can have a fraction over here, it's better to give it as a decimal, and that means we can then show an appropriate amount of significant figures. So yeah, this one here is 1.3 meters per second squared. And you'll see here that I haven't put 1.33333 like on my calculator. I haven't put 1.3 recurring. We tend not to use a recurring symbol in physics, we just round it to an appropriate number of significant figures. Okay. Cool. Right then, rearrange the equation to make v the subject. So I'm going to start with a equals v minus u divided by t. What I'm then going to do is, and this is a nice example of rearranging an equation where you can't just rely on that kind of formula triangle. You've got 4 different things, and therefore you need to be able to have this skill of rearranging equations. The first thing I'm going to do is multiply everything by t. So at is equal to v minus u. And then to get the v on its own, we're going to add u to both sides. So we can say that u plus at is equal to v. And then the final step, just to neaten it all up, we tend to put the thing that we've rearranged on the left. That's the subject of the equation, so we can say that v is equal to u plus at. So that's the first equation. Awesome, yeah, and it's great that okay, so just seeing a few comments here. Again, thank you, Mr. Seaton, for recommending my stuff to your students. And I hope your students are watching this as well. So if your teacher is awesome and Mr. Seaton, then hopefully you're watching this. Arjun put v equals at plus u. Yep, that's correct. It doesn't really matter which way round we have, because we could have v equals u plus at or v equals at plus u. Both of them are absolutely fine. And Jesus Christ, hello, asks what happened if they told you how many significant figures they wanted to. So maybe the previous one here, yeah, if they said give your answer to 3 significant figures, then you just make sure you do that. Okay, so the reason I gave it 2 here, I suppose 1.5 minutes from rest. I think generally 2 significant figures is good enough for most answers. Okay, the next one. This one here, we want to make u the subject. So again, we start, again, I'm just going to write down all the steps. So a equals v minus u over t. We can say that at is equal to v minus u. And then if we add u to both sides, like we had before, u plus at is equal to v. So u is equal to v minus at. Okay, so v is equal to u plus at, or u equals v minus at. So there we go. Hopefully that makes sense. Yeah, there we go. So u equals v plus at. So what I've done here is I've multiplied both sides by t. So we brought the t from here up to here. So then what I've said is that at is v minus u. So that's rearranged that bit. What I've then done is I've added u to both sides. So we've got u plus at is equal to v on its own, which we've got here. And then all I've done is I've taken at away from both sides. So rather than u plus at, I've taken at away from there. So hopefully that makes sense. Okay, for the third one here, to make t the subject, trying to find another colour. So a is equal to v minus u over t. We're going to multiply both sides by t to say that at is equal to v minus u, and then we're going to divide both sides by a so that t is equal to v minus u divided by a. Okay, so we've got three different equations here for different subjects of that equation. Okay, so he said, since acceleration is a vector, is there any need to put a direction? Often, I think it really depends on the question. I think the context of the question really lets you know, but normally you just give it a positive or negative value for if it's speeding up or slowing down. And it's only if they ask you explicitly, you know, saying which direction is the acceleration acting in, would you then actually have to put down the direction as well. Okay, fill in the table with the missing value. So the first one, we want to find the value of v. And it says here that v is equal to u plus at. Now for this one here, that's going to be equal to the value of u, which is 5.0 plus at. So that's 3.0 times 45. And again, if I put it on the calculator, so 45 times 3 is 135 plus 5 is 140. So my value for v, the final velocity, is 140 meters per second. So I've used v equals u plus at for this one over here. We're going to do the same down here. So again, v equals u plus at. So that's equal to 12.8 plus a, which is 24.0, times the time, which is 3.00. So 24 times 3 plus 12.8 is equal to 84.8. And if you've been watching a lot of my live streams, you realise that I tend to use the same amount of significant figures in my answers, my raw values. So that's 3 significant figures, that's 3, and that's 3, so I'm going to give that to 3 significant figures as well. The next one, we're going to find the value of u. So what we can see here is that u is equal to v minus at, which is equal to 66.9 take away a, 11.1 times 2.00. And again, if you've got answers at home, please just put them in. And I can see it's great that Arjun and other people are starting to put answers in. So if you've got an answer, just put it into the comments and you can check if you're right. You know, why not? So the next one is 66.9 take away 11.1 times 2, 44.7 to 3 significant figures is appropriate, so 44.7. We're going to do the same again here. So u is equal to v minus at, so the same equation. So that is 136 take away 10 times 12. So 10 times 12 is 120. 136 take away 120 is just 16. So 16 is 2 significant figures like the raw data that we've got here. Excellent. Arjun is kind of storming ahead in terms of getting all the right answers, which is brilliant. And the final bit over here, we're going to look at t. Now we know that t is equal to v minus u divided by a. So here the time is going to be equal to v, 36.5, take away 23.0, divided by a, which is 135. Okay, so let's try that. So 36.5, take away 23, divided by 135 is 0.1. So I'm going to give my answer as 0.100. So yeah, this one here, I've given it to 3 significant figures like the raw data that we've got as well. Okay, so that's 3 significant figures, just like that is. So 0.1 is correct as a number, but 0.100 is even more correct. Okay, and the last one we're going to do the same thing again. The time is going to be equal to the change in velocity, so 423.3 take away 3.5 divided by 1.4. So I'm just going to rely on my calculator for this. and that's 299.857, so that's going to be 300. There we go. Hopefully that makes sense. 299.9. Yeah, but what I've done here is I've just rounded it, I suppose, to two significant figures, although it could be 1 or 3, you can't really tell. But yeah, so 299.9 is rounded to 300. So that one there, very simple. All we're doing is we're using the equation A equals V minus U over T. We've rearranged it into this form, or this form, and then we're just plugging our numbers in. Hopefully that's all making sense. All good? Right. So we now come on to some questions. So we've got a question about Iron Man. We've got a question about a teacher and a wheelie bin. So yeah, let's just do this. So first of all, Iron Man decides to test how fast he can accelerate vertically upwards. He starts from the ground at rest and gets to a velocity of 230 meters per second in 12 seconds. So calculate the acceleration. So again, if you've got the questions at home, please put your answers down. The acceleration is equal to V minus U divided by T. So his final velocity is 230, but he starts at rest, and that took him 12 seconds. So all we've done is started to identify the right information from in the question there. We've then written out the equation, put in our numbers. So 230 divided by 12 is equal to 19.17. So for this one here, that's given to two significant figures. So this one here, I would say, is 19 meters per second squared. So that's probably the appropriate way to put the answer for this question. Explain whether if Iron Man were to change direction whilst travelling at a constant 230 meters per second, he'd be accelerating. So here, Iron Man's initial speed was 230, final speed was 230. Have they accelerated? Yes, they have. Because what they've done is they've changed direction. So the answer is yes, he would accelerate because velocity changed. Okay, so initially they might be going this way, a short time later they might be going this way. Now they might still be going at the same speed, but their velocity, because it's got a direction as well, has changed. So yes, he'd accelerate because velocity changed because he changed direction. Okay, so hopefully that makes sense. So yes, but yes, he would. Okay, after making some adjustments, Iron Man repeats his test. This time he gets to a velocity of 260 meters per second. So he's got a lot faster, which is good, but it takes him 14 seconds. So it's taken him longer to get to a faster velocity. Has his acceleration improved? So again, A is equal to V minus U over T. His final value is 260, again starting at 0, divided by 14. So now, 260 divided by 14 is equal to 18.57. Now, initially, we said that their acceleration was 19 meters per second squared, and now the answer is 18.57, which would still round up to 19 meters per second squared, but that's going to be a lower value, and that's why it's important sometimes to write down your kind of the intermediate answers that you might get to several significant figures. So I would say, has it improved? The answer is no. Okay, so it hasn't improved. There we go. Genius has had enough. Okay, no, you are going to be good at physics, because Genius, if you just keep slogging away at doing this stuff, you will get it eventually. And it might be you don't get it today, but maybe you have a go at the questions today, you get some of the answers, and maybe you come and revisit similar questions in a couple of weeks' time, and you might just find that you're picking bits and pieces up, and it takes a long time. Also, Arjun put a fantastic answer in the comments to this part bit here about why he would be accelerating even though he was going at a constant speed. And I would say, has it improved? No, because its acceleration is not as quick as it was previously. Okay, right, so the next one. A teacher attaches a gas cylinder to a wheelie bin. So this is very much to kind of make like you can sit in the wheelie bin and then you can basically propel yourself along. She opens the cylinder, releasing the gas, which accelerates the bin at a constant rate of 1.2 meters per second squared. The bin reaches a final velocity of 23 meters per second. Calculate the time the bin takes to accelerate to 23 meters per second squared. So, thinking back what we had before, we can say that time is equal to the change in velocity divided by the acceleration. Now, do we know the final speed? Yeah, the final speed, v, and I'm going to put v is 23 here. So 23 meters per second, initially started at 0, they were static before that gas had been released, and the acceleration is 1.2. So 23 divided by 1.2 is 19.17, so that's 19 seconds. Okay, so that's the answer. It's taken a teacher 19, or you could say 19.2, but I'm going to give it to two significant figures like this as well. So 19 seconds for that bin to accelerate. And to be honest, yeah, actually Arjun's saying, yeah, in an exam they'd allow any rounding unless specified, I believe. Yeah, I think that's true. Basically, if you put that in an exam, bear in mind this is GCSE and they want you to do well. The people marking your test, they, if they see an answer like this, where they've clearly seen that you've maybe identified bits from the question, you've chosen and rearranged the appropriate equation, and you've put the right bits of data into it, and you've got an answer, they're not going to penalise you lots and lots of marks. They're not going to say that's wrong, but I want you to get into good habits and be not just correct, but as correct as you possibly can be. So this one here, about 19 seconds. So the teacher, she wants to increase the bin's final velocity. She pushes the bin so that it is travelling at an initial velocity of 3.6 meters per second, and then the acceleration is still 1.2. So we want to calculate the final velocity. So we can say that v, actually what did I use? I think I used purple, did I? V is equal to u plus at. So the idea being that even though the acceleration might be the same rate of acceleration, if the bin is initially moving before that gas is released, it might get to a higher final velocity. So the final velocity is going to be equal to the initial velocity, which is equal to 3.6, added to the acceleration, 1.2, times the time, which is 20. So 1.2 times 20 is 24, added to 3.6 gives an answer equal to 27.6. So again, I'm going to round this to 28 meters per second. There we go. So that's pretty quick. I mean, if you're in this bin, or even if you saw it going flying past, going at 28 meters per second, yeah, that's pretty fast if you imagine what that might be like in real life. But, you want to go faster. So still unhappy with the velocity, she tweaks a gas cylinder. So basically, if you let more gas out per second, there's going to be a greater rate of change of mass. So you might get a higher value for the acceleration, but the gas in there isn't going to last as long. So here we go. So we've got the acceleration is 1.5. The time is 15 seconds, and the initial value is 4.8 meters per second. So is the final velocity going to be bigger or lower than that previous answer of 27.6? So again, we're going to use the same equation to say that v is equal to u plus at. The value of u is bigger because now it's 4.7, added to a bigger acceleration of 1.5, but for a shorter amount of time. So 1.5 times 15 plus 4.7 is equal to 27.2. So therefore, and this symbol here means therefore, so it's like 3 dots. So therefore, not as fast. So this time, previously it got to about 27.6, now it's got to 27.2 meters per second. So not as fast as before. Calculate how fast the bin would have to be initially travelling for the bin to reach 30 meters per second in 15 seconds. So now what we're going to be looking at is u. Okay, so we can say that u is equal to v minus at. So initially travelling is how fast it was going. We've got a final velocity of 30, a time of 15, and we know that it accelerates at 1.5 meters per second. And therefore that's going to be equal to 30 take away 1.5 times 15. So 30 take away 1.5 times 15 equals 7.5. So this one here, 7.5 meters per second, is at the initial velocity of that. Excellent. Some people are saying this is just too easy. Yeah, fair enough. However, yeah, there we go. So hopefully that makes sense for the last bit there. And it's great to see that Arjun and Masood, hopefully I've not kind of butchered your name there. Hopefully everybody there is making sense of the stuff here. And yes, you know what, some of these questions are straightforward, but you want to get the basic questions sorted, get really good at them. And if you want to have more challenge, there are loads of places. Hang on there 1 second, I'm going to show you what I mean. So this book over here, if you're finding this easy, but bear in mind some people might not be, if you haven't done this at school before, if this isn't your thing, if you're doing it for the first time, there's some difficult questions here. However, if you are finding that this is all straightforward, which some people it might be, this book here, the GCSE Isaac Physics book, is excellent. And if you want to find, let's have a look. So let's say we wanted to look at acceleration. So this one here, page 27. Let's have a look. Again, there are questions here about acceleration. A equals v minus u over t, all the kind of good basic stuff. But, you know, there's loads of questions here. And again, if you have a go at these questions on Isaac Physics, then this is the place to do it. So a lot of them actually start out quite simply. So, you know, just filling in values here for the acceleration, the velocity after how many seconds, so maybe 3, 6, 9, 12, 15, 18. Okay, this one over here, if you go and Google Isaac Physics, actually, tell you what you might want to do is, I made a video about this the other day for the pre-A-level kind of course, so that students who are maybe thinking about doing A-level physics next year, so this is our current year 11s, I made a video about Isaac Physics. So if somebody maybe out there could just find a link, it's one of the videos I put up on Saturday, I think it was, I put the video up on my YouTube channel on Saturday. I made a video about Isaac Physics and actually how to log into it and how to use it. So yeah, what I will do though is say that, you know, if you want to get good at physics, if you want to guarantee, you know, a grade 7 or 8 or a 9, you know, if you want to get the grade 9s, this is a book that if you just start doing it now, you will get loads and loads of practice in and you will properly understand the physics. So that is the end of the lesson today. I hope everybody is doing well at the moment. I will see all of you again tomorrow when we're going to be looking at velocity time graphs. Now, to understand a velocity time graph, you need to know about these acceleration calculations, about the change in velocity divided by time, which is often the gradient of a velocity time graph. I'm going to do some extended stuff there about the area underneath that velocity time graph representing the displacement or the distance travelled. So thank you so much for watching. I hope everybody is safe and well, and it is hard to stay motivated. I appreciate it's been a long time since you were at school and a long time since you might go back. But hopefully some of the stuff here has helped about acceleration. So until tomorrow, thank you very much. Are you studying GCSE Physics? Here at Physics Online, I've made hundreds of videos for every aspect of every course, all organised by exam board and then by topic. For a small one-off payment, you get access for 3 years, and at £9.99 it's far cheaper than you might expect. That's the same price as 3 pod copies or 3 Big Macs. Gain access to all videos to learn the physics that you require for your exams. Put simply, for less than a tenner, you get on-demand access to all the videos that you'll need in GCSE Physics.